Hi everybody, I wanted to just talk about section 10.2 on hypothesis tests for a population proportion. So these will be the objectives. We want to explain the logic of hypothesis testing, test the hypothesis about a population proportion, test hypotheses about a population proportion using the binomial probability distribution. So the first objective, objective 1, we want to explain the logic of hypothesis testing. So as an example, let's say a researcher obtains a random sample of 1,000 people and finds out that 534 of them are in favor of banning cell phones while driving. So in this case, the population proportion, which is denoted by P with this little arrow above it, again that's P hat, is equal to 534 divided by 1,000. So does this suggest that more than 50% of the people favor the policy, or is it possible that the true proportion of the registered voters who favor the policy is some proportion less than 50%, and we just happen to, our sample just happened to have a majority in favor of the policy? In other words, would it be unusual to obtain a sample proportion of 0.53 or 4 or higher from a population whose proportion is 50%, and what is convincing or statistically significant evidence? When observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant. When the results are found to be statistically significant, we reject the null hypothesis. So to determine if a sample proportion of 0.534 is statistically significant, we build a probability model. In this case, the sample size times the probability of success times the probability of failure. If it's greater than 250, and the sample size n, in this case 1,000, is sufficiently smaller than the population size, we can use the normal model to describe the variability in the sample proportion, p hat. So the mean of the distribution of p hat is mu sub p hat equals 0.5, and the standard deviation in this case is given by p times 1 minus p over n, so in this case that would be 0.016. So the sampling distribution of the sample proportion would be something like this, where this would be one standard deviation away from the mean. And so we may consider the sample evidence to be statistically significant or sufficient if the sample proportion is too many standard deviations, say 2 for example, above the assumed population proportion of 0.5. So recall that our simple random sample yielded a proportion of 0.53. So putting this into the formula for z, where again p hat now is the value and this would be our mean and this would be our standard deviation, plugging into this formula we get a z value of 2.15, and the standard deviations above the hypothesized proportion of 0.5. Therefore, using our criterion, we would reject the null hypothesis because this z-score is too high, right? This value here is too far away from this value. Why does it make sense to reject the null hypothesis if the sample proportion is more than 2 standard deviations away from the hypothesized proportion? Well, remember that the area under the standard normal curve to the right of z equals 2 is equal to 0.0228, right? That was because of the empirical rule. And remember that an event is unusual if it's less than 5%. So if it's in this region, it's a pretty unusual occurrence. So if the null hypothesis were true, the population proportion is 0.5, then 1 minus 0.0228, which would equal 0.9772, is equal to 97.72% of the sample proportions will be less than 0.532. And so only 2.28 of the sample proportions would be more than 0.532. Now there are sort of two different ways we can test hypotheses. We can use what's known as the classical approach and the p-value approach. So let's look at the classical approach first. So if the sample proportion is too many standard deviations from the proportion stated in the null hypothesis, we will reject the null hypothesis. An alternative way to test whether a hypothesis is true or not is using the p-value or probability value approach. And if the same proportion of getting a sample proportion as extreme or more extreme than one obtained in the small is small under the assumption that the statement in the null hypothesis is true, we reject the null hypothesis. So as far as the logic of the p-value approach is concerned, the second criterion we may use for testing hypotheses is to determine how likely it is to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5. If the sample proportion of 0.534 or higher is unlikely, right, or unusual, if the probability of that happening is less than 5%, right, we have evidence against the statement in the null hypothesis. Otherwise, we do not have sufficient evidence against the statement in the null hypothesis. So we can compute the probability of obtaining a sample proportion of 0.534 or higher from a population whose proportion is 0.5 using the normal model. So again, we did this earlier. Right? We calculated this, and the probability in this case is 0.0152. So in other words, you can basically compare either the number of standard deviations it is away from the mean, or with the p-value approach, you compute the actual probability. Now in practice, this may be difficult to compute using a table, because remember, the table's in the back of the book. You basically calculate the z-value first and then look up the corresponding probability. So you might need to use StatCrunch or something to compute this probability value. So this p-value approach wasn't used so much before the advent of modern computers, but now since we can compute those probabilities relatively easily, we can use this approach. So this value here that we obtain is 0.0158 is called the p, or probability value, which means that about 2 samples in 100, given a sample proportion is higher than the one we obtained if the population proportion is really 0.5. Because these results are unusual, we take this as evidence against the statement in the null hypothesis. So as far as doing hypothesis testing using the p-value approach, if the probability of getting a sample proportion as extreme or more extreme than the one obtained is small under the assumption of the statement and the null hypothesis is true, we reject the null hypothesis. So let's take a look at objective 2 on test hypothesis about a population proportion. So the best point estimate, the population, the proportion of the population with a certain characteristic, if you remember, is given by p hat. That's just a number in your sample n divided by, or divided into the number that have a particular characteristic. So the sampling distribution of p hat, if you remember, is approximately normal, with the mean equal to the value that's given, and then the standard deviation, again, given by p times 1 minus p over n. And remember that this is only true if the following conditions are satisfied. So the sample has to be random, n times p times 1 minus p has to be greater than 10, and the sample values are independent of each other. If these conditions are not true, then this may not, this information up here may not be true either. In most cases, you can, I think, assume that the conditions are satisfied, but you might want to verify those, especially if the problem asks you to do so. So as far as testing a hypothesis regarding a population proportion, we can use the steps that follow, provided that the sample, again, is obtained by simple random sampling. This value is greater than 10, and the sample values are independent of each other. So step 1 would be to determine the null and alternative hypotheses. And hypotheses can be structured in one of 3 ways. And this is basically the same thing listed on the bottom of page 487 and the top of page 488 in your book. So again, we can have a two-tailed test, left-tailed test, or right-tailed test, as we saw in 10.1. And then we select a level of significance alpha based on the seriousness of making a type 1 error. Typically, alpha will be equal to 5% unless otherwise stated. If it's something where a type 1 error might seriously injure or harm someone, you might want to make alpha a little bit smaller, like 1%. But unless otherwise stated, alpha will always be 5% or 0.05. So you compute the test statistic like we did in the last example, if we're using the classical approach. And again, if it's a two-tailed test, then basically, if your computed statistic falls in this region over here, or this region over here, then you would reject the null hypothesis. For the left-tailed test, if your test statistic falls in this region, again you would reject the null hypothesis. And for right-tailed test, if your calculated value z sub 0 falls in this region, you would reject the null hypothesis. So that's the classical approach. And so basically what I just said, if z sub 0 falls in the critical region, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. With the p-value approach, you would calculate the z-score again, but in this case, you don't compare the z-scores to the z-alpha value. You could use table 5, or again, what's probably better in this case is use StatCrunch because it can give you more accurate value. So if in this case, if the p-value is less than alpha, we reject the null hypothesis for the p-value approach. And then just make sure that you state the conclusion, whether you accept or reject the null hypothesis, make sure that you clearly state your conclusion. So as an example, let's say that in 1997, 47% of Americans said they did not trust the media. So in a 2007 poll of 110 adults nationwide, 525 stated that they did not trust the media at this level of significance. And so is there evidence to support the claim that the percentage of Americans that do not trust the media has increased since 1997? Well, so first of all, we need to know if we can conduct the test. So we need to make sure that the conditions are satisfied, which they are. And then set up your null and alternative hypothesis. And this is our level of significance. So calculate the proportion. Calculate your test statistics. So this would go in here. This would go in here. Work this out, you get that. And then it depends on whether we want to use the classical or the p-value approach. So if you use the classical approach, you'd need to compute z over alpha in this case and compare it to this test value. So with the classical approach, the level of significance is 0.05. So z of 0.05 is this number. How does that compare to the value that we calculated? So in this case, the test statistic is greater than the critical value, so we reject the null hypothesis. If you were to use the p-value approach, in this case you'd calculate the same statistic and then calculate the probability that z is greater than that value, again either looking it up in the table or calculating it using StatCrunch or something. Effectively the probability here would be 0. So since the p-value is less than the level of significance, we reject the null hypothesis. Step 6, make sure that you state the conclusion here, and I don't know if you need to state the level of significance here, but you should say something like there's sufficient evidence to conclude that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. Objective 3, we want to test hypotheses about a population proportion using the binomial probability distribution. So remember, for sampling distributions to be approximately normal, we require that this be true. So if the requirement is not met, we stated that an event is unusual if the probability of observing the event was less than 0.05. So this is based on the p-value approach. We use the same approach to test hypotheses regarding a population proportion for small samples. So remember that for small samples, the normal distribution can be approximated by the binomial distribution. So for example, let's say in 2006, 10.5% of all births in the United States were to mothers under 20 years of age, and a sociologist claims that the births to mothers under 20 years of age was decreasing. So she conducts a simple random sample of 34 births and finds that 3 of them were to mothers under 20 years of age. The sociologist test the sociologist's claim at the 0.01 level of significance. So determine the null and alternative hypothesis, determine whether the conditions are met, compute the p-value, and then if the p-value is less than the level of significance, we reject the null hypothesis. So in this case, this would be your setup. So in this case, we get that this is less than 10, so the sampling distribution is not approximately normal. So calculate your p-hat, and so we can use a binomial approximation for this. So going back to one of the previous chapters, we would get that the probability in this case would be 0.51. And so So the p-value is greater than the level of significance, so we do not reject the null hypothesis. Okay, well I hope that